Okay, let's dive into this. Welcome to today's explainer, where we're going to take a really fascinating journey through the complete end-to-end life cycle of modern cloud infrastructure. We aren't just talking about writing code today. We're talking about how that code actually comes to life, how it grows, how we keep it safe from our own, inevitable human errors, and finally, how we responsibly tear it down. It is a full journey from creation all the way to destruction. So here's our roadmap for this explainer. First up, rapid full-stack deployment. Second, Kubernetes control at scale. Third, we'll look at managing Terraform state. And fourth, precision destruction and cleanup. All right, kicking things off with Section 1, rapid full-stack deployment, bringing apps to life with AWS Amplified Gen 2. Now, to get apps off the ground super fast these days, developers are turning to platforms like AWS Amplified Gen 2. Because, honestly, instead of manually configuring dozens of totally separate services, Amplify just simplifies the whole shebang, building, deploying, and hosting full-stack apps. Think about building a modern React to-do application. You don't just need front-end hosting, right? You need AWS Cognito for secure user authentication so people can actually log in. You need DynamoDB to store those to-do list items. Well, Amplify brilliantly binds all these moving parts together, the front end, the back end, the APIs, even custom domain setups, into just one single manageable platform. And this brilliantly illustrates the true power of a frictionless CI/CD pipeline. Continuous integration and continuous deployment. The process is just incredibly streamlined. First, you just connect your GitHub repository directly to the AWS console. Second, Amplify automatically detects that, hey, you're running a React application, and it knows exactly how to build it using standard Node Package Manager commands. And third, boom, it builds and deploys the app automatically. The absolute magic here is that once this pipeline is open, a simple code commit, like literally updating a single line of code in your index file from version 7 to version 8, instantly triggers a new build. Within minutes, the live application is updated for the whole world to see, with absolutely zero manual server configuration required on your part. But of course, with this incredible speed comes our first major theme of the day, and that is safety first. When you're moving this fast, how do you stop developers from accidentally corrupting the main database while they're just testing new features out on their laptops? Well, the solution is the Cloud Sandbox. On one side, we have our main app environment, which is permanently hooked into our production DynamoDB tables and Cognito user pools. But on the other side, the Cloud Sandbox. By running just one simple command, npx ampx sandbox, developers get a completely isolated local environment. It creates an exact replica of the cloud resources that they can test against locally, entirely segregated from the main app. So if a developer totally breaks the database in the sandbox, the production environment doesn't even blink. Moving right along to Section 2, Kubernetes control at scale. This is all about organizing and securing your containerized infrastructure. So as your infrastructure scales up, you might have hundreds of resources running simultaneously. So I want to ask you this. When you look at a massive list of servers, how do you actually know which server is safe to delete? Well, if you don't know the answer to that question, things can go wrong very, very quickly. Here's a visceral, real-world horror story from our sources. In one organization, a developer was asked to delete a development instance. But because nothing was clearly marked, the developer accidentally deleted the EC2 instance belonging to the staging environment. Instantly, the entire quality assurance team came running to the DevOps engineers in an absolute panic because their whole testing environment just vanished into thin air. A true resume-generating event for sure. Now, this massive mistake happened for one simple reason: a total lack of proper identification. The solution in Kubernetes, and really in cloud platforms like AWS in general, is using labels and selectors. Labels are explicit key-value pairs that you just attach to your resources. For example, you tag a pod with nv equals dev for development or nv equals prod for production. Selectors are then used to filter these objects. So instead of guessing which pod to manage or delete, you write a command that tells Kubernetes, hey, show me exactly the resources where the environment equals development. By filtering out production resources entirely, you mathematically eliminate the risk of accidentally taking down your live application. It's a lifesaver. Now, what's really interesting about this slide is how Kubernetes manages safety beyond just labeling using a really cool concept called daemon sets. Typically, you might use a replica set to launch pods, but a replica set might schedule 2 or 3 copies of a pod on a single node just based on resource availability. A daemon set, however, guarantees that exactly 1 copy of a pod runs on every single worker node in your cluster. Why does this matter? Well, think about cluster-wide safety tasks like an antivirus scanner. You definitely don't need 3 antivirus scanners on one server, and you absolutely cannot afford to have 0. You need exactly 1. Plus, if your cluster scales up and adds a brand new worker node, the daemon set instantly and automatically deploys that antivirus pod to the new node, ensuring there are literally 0 security blind spots. All right, let's jump into Section 3, Managing Terraform State. Keeping infrastructure logic consistent and uncorrupted. Imagine you've got a large team of developers, and they're all writing infrastructure code. What happens if 2 engineers, let's call them Alice and Bob, run the Terraform apply command to update the infrastructure at the exact same millisecond? Well, the answer is a massive risk of severe state file corruption. If Terraform tries to write overlapping changes to its core tracking files simultaneously, you get total chaos and massive inconsistencies. So to prevent Alice and Bob from crashing the whole system, Terraform relies on state locking. Think of this just like a phone call. You can only actively talk to one person on a specific phone line at a time, right? If someone else tries to call you, they get a busy signal. It's the same here. When Alice runs her update, Terraform requests a lock. If it's a local backend, it generates a .log.info lock file. If it's remote, it uses the locking features of a service like AWS S3. While Alice's update is actively writing, Bob's attempt will just return an explicit error stating, "Error acquiring the state lock." Only when Alice's update is perfectly finished is the lock finally released, allowing Bob to proceed safely. So the crucial point is that you must never, ever manually edit a Terraform state file with a text editor to fix an issue, because you bypass all of these safety mechanisms we just talked about. Instead, Terraform provides these specific, incredibly safe commands. State list shows you exactly what resources are currently tracked. From there, state MV is fantastic for renaming a resource in your code without Terraform thinking it needs to destroy the old one and build a whole new one. Want to leave the server running but stop tracking it? State RM lets you tell Terraform to stop managing an asset without physically destroying the actual server in the cloud. And if you just need to inspect things, state pull and show allow you to inspect the details and read values securely. It is surgical, precise management. Which brings us to our final part, Section 4, Precision Destruction and Cleanup, tearing down resources safely and avoiding runaway billing. Look, when you're done with a project, you need to tear it down. But you have to be careful here too. If you simply run a standard Terraform destroy, Terraform will ruthlessly wipe out every single resource defined in your entire working directory. But what if your directory contains both an experimental DigitalOcean droplet and a vital AWS EC2 instance that you really need? You obviously only want to delete the experiment. By using Terraform destroy target and specifying the exact resource block, like DigitalOcean_droplet.doDemo, you perform a surgical removal. Terraform removes only that specific droplet and leaves your vital AWS EC2 instance completely untouched. Let's move to and see how this builds a comprehensive teardown strategy, taking us all the way back to where we started with our AWS Amplify app. Your final cleanup checklist requires real precision. You can't just delete the front-end code and call it a day. You must deliberately delete all cloud sandboxes. You must go into the general settings and remove the main Amplify application itself. You have to ensure that the backing resources, the DynamoDB tables actually holding the data, and the Cognito user pools managing the logins are completely wiped. And finally, you must delete your DNS configurations, like your Route 53 hosted zones. Skipping any of these steps leaves orphaned resources quietly sitting there generating runaway cloud billing, and nobody wants a surprise bill at the end of the month. So from spinning up a full-stack web application in seconds, to orchestrating it safely at scale, to protecting the very code that defines it, and finally, tearing it down with surgical precision, you now understand the complete cloud infrastructure lifecycle. With deployments, orchestration, and destruction fully automated and protected by built-in safety rails, the real question is, what will you build next? Thanks so much for joining me on this explainer, and I will catch you on the next one.